All right, team, welcome. Your mission, should you choose to accept it, is to re-engineer one of the toughest vehicles on the planet, the cement mixer. We're going to take this diesel-guzzling workhorse and turn it into a silent, efficient, hybrid-electric powerhouse. Okay, let's get into it.
First things first, you have to understand the stakes. This isn't just about saving a little fuel, it's about solving what we call concrete anxiety. That's the cold sweat every operator gets, thinking about what happens if the power to that drum cuts out. Because if that drum stops turning, you don't have a truck anymore. You have a 30-ton block of solid concrete. That's a catastrophic, right-off-the-vehicle failure. Our entire design has to prevent that, period.
So here's the fundamental problem we're fixing. A traditional diesel mixer has to keep its massive engine running for hours on end just to spin the drum. I mean, think about that. Up to half its fuel is just wasted sitting there making noise and pollution. Our new way completely separates driving from mixing. The result? A silent, zero-emission workhorse on the job site.
So, how do we actually do this? Well, it's not as simple as just throwing a battery in. We need a really elegant, robust engineering blueprint. So let's break down the architecture we're going to use.
Our blueprint is called the P2 Hybrid Plus ePTO architecture. Now, I know it sounds complex, but the idea behind it is brilliant. We basically sandwich an electric motor, that's the P2 motor, right between the engine and the gearbox. That lets us drive the truck with electricity. Then, we give the mixing drum its own, totally separate electric motor. We call this the electric power takeoff, or ePTO. This is the absolute key, you see. The drum's rotation is now completely decoupled from the engine.
And this setup gives us some incredible flexibility. It works in 4 different modes. In the city, you can run in pure EV mode, totally silent. When you hit a steep hill, that P2 motor kicks in to help the diesel engine. Now, at the job site, this is the magic part. The engine shuts off completely, and the battery powers the drum in stationary ePTO mode. And on the way back down a hill, every time the driver hits the brakes, that P2 motor flips into a generator, capturing energy to recharge the battery. It's a full, intelligent power cycle.
Of course, none of this is possible without a serious power source. So now, we've got to engineer the heart of the system, the high-voltage battery. And this is where the tough, real-world challenges of a construction site really come into play.
Our first big decision is the battery chemistry. And frankly, it's not much of a choice. While NMC batteries might pack a little more punch in terms of energy density, for a heavy-duty vehicle that gets shaken and rattled and abused for over a decade, there's only one answer: lithium iron phosphate, or LFP. It's just fundamentally more stable, way less prone to thermal runaway, and it can handle thousands more charge cycles. In this world, safety is non-negotiable, so LFP is mandatory.
So, how big does this energy tank need to be? Well, we ran the numbers on a typical day. That's about 4 to 6 delivery trips. And it shows we need right around 60 kilowatt hours. That's enough juice to power that drum for an entire shift, making sure we never, ever have to deal with that dreaded concrete anxiety.
But, you know, a battery is just a box of chemicals if it doesn't have a brain. That's the battery management system, the BMS. Think of the BMS as the battery's own personal doctor, constantly checking its vital signs. It tells us the state of charge, which is basically the fuel gauge. It tracks the state of health, which tells us how long it's going to last. And, most critically, it defines the state of function, the safe limits for power going in and out at any given second.
And this brain lives inside a fortress. The battery pack is liquid-cooled to handle the insane power needed to start a drum full of wet concrete. It's all housed in a reinforced steel case, and the entire thing is engineered to survive the brutal, non-stop vibration you get on a construction site. We're talking meeting the incredibly tough ISO 16753 standard. This isn't a car battery. It's an industrial power pack built to last 15 years in the harshest conditions you can imagine.
Okay, so we have the power, but with all that power comes a huge responsibility. Our most critical mandate is taming this 400-volt system and making it absolutely foolproof for anyone who operates or even services this truck.
Our number one safety net is something called the High-Voltage Interlock Loop, or HVIL. And the best way to think about it is like the safety switch on your kitchen blender. The blades won't spin unless that lid is perfectly clicked into place, right? The HVIL works the exact same way. It's a separate, low-voltage circuit that runs through every single high-voltage connector. If even one of those connections isn't perfectly seated, the system just refuses to power up. Simple as that.
And the real genius here is in the mechanical design. It's a principle we call last mate, first break. Inside every connector, the little HVIL pins are physically shorter than the big power pins. So when you plug it in, the big power pins make contact first, but nothing happens. It's only when you push it all the way in that the shorter HVIL pins connect, which tells the system, okay, we're secure, go live. And when you unplug it, the reverse happens instantly. The HVIL breaks first, the system immediately cuts the high voltage, and then the power pins disconnect from a totally dead circuit. No sparks, no danger. It's brilliant.
But there's another hidden danger lurking in this system. The motor controllers have these massive capacitors inside, and if you were to just connect the battery directly, those empty capacitors would look like a dead short to the battery. For just a split second, you'd get a surge of current of maybe 2,000 amps or more. That's enough to literally weld the main power relays shut and cause a catastrophic failure.
So how do we stop that massive surge? The solution is a really elegant pre-charge circuit. Before closing the main power relays, the system first closes a smaller relay that sends all that power through a simple resistor. This resistor gently fills up the capacitors. It's exactly like filling a water balloon with a thin straw instead of a fire hose. Once the voltage is stable, then the main relays close safely, and the system is ready for work.
So after all this engineering, the hybrid architecture, the bulletproof battery, the layers and layers of safety systems, what's the payoff? What do we get for all this work? Let's look at the results.
Mission accomplished. We have cut overall fuel consumption by up to 50%. At the construction site where these trucks spend most of their day, the local emissions are zero. And the noise? That constant grinding drone of a diesel engine is gone, replaced by the quiet hum of an electric motor. That makes our cities way more livable.
And this is where the success of this mission becomes truly transformative. This modular P2 plus ePTO system is so much more than a fix for one vehicle. It's a blueprint for the future. You can take this same architecture and scale it to electrify an entire class of heavy-duty vehicles. Think garbage trucks, bucket trucks, mobile cranes. We haven't just built a better truck, we've created a template for a revolution.
By solving one of the absolute toughest challenges in the industry, we've basically unlocked the door to a cleaner, quieter, and way more efficient future for all heavy equipment. So really, the only question left is, what giant do we tackle next?